Welcome to the next video. We're going to talk about solvent masking now. So we're going to use the same data set as in the video number 7, so disordered toluene. And thing that you have to remember when using solvent masking is that it's kind of a last resort. You should only use it if you cannot model your solvent, if it's so terribly disordered you can't do anything. And basically, you can do it when it's so disordered that basically modeling that disorder would be like fitting a chemdraw to a big blob of electron density. Then it makes sense to use solvent masking. But in cases like that one, where we were able to model it very quickly, we should absolutely not use it. But we use this data set to show you how to use solvent masking. So first thing we need to do is to, well, delete solvent. So we delete that molecule, we delete that molecule, and we do the refinement. Now we have a model that doesn't have any solvent. Here we can see that there's a huge peak of maximum electron density and large groove. Yeah, we deleted important atoms, so that's why. So we can do solvent masking in two ways. Firstly, we can use bypass. It's very convenient to use from OLEX, it's the easiest way. We can also use Platon. And Platon is, well, it works in a similar way. There's just a little bit more clicking, but we can do both ways. And I think, usually in my experience, it's worth to try to do it both ways and then compare the results and use the better one. So there were some structures where OLEX worked perfectly fine, but there were some cases where Platon gave me better results, and also the other way around. So yeah, it's something to play with. So okay, we have a model which doesn't contain any solvent. We can do now use mask, and we refine. You can see that parameters already got better. We don't have this terrible maximum of electron density, and we have a table. So it says that we have like 3 voids, 2 very, very tiny ones with 0 electrons inside, and we have 1 void that contains 49 electrons. And 49 electrons is very close to one toluene molecule. One fully occupied toluene molecule is 50 electrons. So you can see that in this void, there is basically the toluene molecule that we managed to model previously. It's always a good idea to update the mask before finalizing structure. Okay, let's untick it, do extra refinements, 20, let's say. Yeah, looks good. It's still orange, so we can keep refining, but you can see that basically parameters are very close to those that we managed to get without solvent masking. Also, in general, you shouldn't do solvent masking, for example, when it's important for charge balance. So you shouldn't do that for anions that you have in your structures. But then, of course, when you have very large supramolecular structures and solvent and counterions are terribly disordered, like sometimes, like we have to do that, right? But in general, don't do that. Also, never do solvent masking on things that are bound to the main molecule. For example, if you have some supramolecular complex that has a template inside, do not try to do masking on the template. It's just not something that should be done. Okay, so the last thing that's left is to basically describe in the CIF file that we used solvent masking. It is by default put in the CIF file by bypass, by OLEX, but I think it's always a good idea to also go to report. You can go to diffraction, and either in special details or refine special details, you can write something like, I don't know, solvent masking was necessary because of large amount of diffuse electron density corresponding to disordered solvent that couldn't be modeled. Solvent masking procedure indicated voids with number of 50 electrons, which is close to a value of 49 expected for toluene, or the other way around, sorry. Yeah, so that's basically it. So let's come back to the initial model. Let's not use mask. And now I will show you how to use Platon or Platon. I'm not sure how is it pronounced in English. I think Platon in English. Platon would be in Polish. Okay, so we need to have Platon or Platon installed. So we click this Platon icon. And now we have to click squeeze. Okay, it did some calculations, 6 voids. Now it will calculate some electron density, model without and with solvent masking. So what we can do now, we can close that, and there should be a file which contains SQ file, ins file. So there's SQ file, which is an ins file. So it means that after basically one round of squeeze, so we can use it for a new refinement. Just make sure that the HKLA file is correct. It should also be the one after squeeze. Yeah, and I'm not sure why does it say here use Olex. No, we're not using Olex mask. Refine. Oh, maybe we should. Okay. Seems like Olex now has direct access to Platon. Okay, so now we can, again, if we want to repeat the same thing, which I think is a good idea to always do, we can go to Platon again. Okay. It's a little bit different number of electrons per cell. And close that. And now we have, after 2 rounds of squeeze, we have file which is SQ. So we're going to the ins file again. Yeah, looks like Alex changed something in the meantime, but it's okay. SQ. And now we have the same result as, I mean, very similar results. We have one big void, 51 electrons in this case. Yeah, so good. Let's do more refinement cycles, say 20. And it's almost done. A bit more cycles to make all of these green. So that's basically how it works. And again, I would advise to write in the CIF file also separately that we use solvent masking. And also it should be also indicated somewhere, for example, in the supporting information file where we describe how you dealt with crystal structure, because essentially if someone is not a crystallographer, it might be difficult for that person to find that information in the CIF file. But if you just put it in the supporting information or also in the main text that you had to use solvent masking, then it's all legit and fine. So that's all I wanted to show you. I hope it was useful. Thank you very much. See you next time.